Course 3, Lesson 66, we are looking at special right triangles. So we've talked about right triangles a lot before with the Pythagorean theorem, but in this lesson we are looking at very specific ones that have angles of 45, 45, 90, or ones with 30, 60, 90. So let's first look at these two triangles. So the first one, 45, 45, 90, this is a triangle that is isosceles because of those two same angles, we have two same sides. And the hypotenuse is the odd one out. Okay? And then we have a 30, 60, 90 right triangle, where this one has all different angles, therefore it has all different sides, so it is scalene. Now something to note is how these angles work is if we have a small angle over here, it is across from the smallest side. 60 degrees here, so middle angle, is across from the middle side. And biggest angle, 90 degrees, is across from the biggest side. Something to note so that you know where things are, especially when we get into some of these patterns. The first pattern that we're going to look at is this 45, 45, 90. Now, when we do this, this actually connects a lot to higher math, things in trigonometry, and therefore things in calculus. And we always base our triangles on having our starting side at 1 unit. 1 unit. When we do that with our 45, 45, 90 triangle, if our leg is 1, then the other leg is 1 because this is isosceles. They're the same. Now, if we plug this into the Pythagorean theorem, we will see that we have 1 squared plus 1 squared is equal to c squared because we don't know my hypotenuse. So if I do 1 squared plus 1 squared, that's just 2 is equal to c squared. So c has to be equal to the square root of 2 because we square root each side to get c by itself, meaning that our hypotenuse is the square root of 2. The question is, does this pattern continue if maybe I change the side lengths to 2? Maybe I start with 2 here instead of 1. Well, let's plug it into the Pythagorean theorem. We get 2 squared plus 2 squared is equal to c squared. Okay, so 4 plus 4 is 8 is equal to c squared. So c is equal to the square root of 8. Now soon we will be looking at how to simplify these radicals. But just know that we could split this into 4 and 2. And with some properties with our radicals, we can actually split that apart and say we have the square root of 4 times, I can simplify that square root of 4 to say that's 2 times the square root of 2. Interesting how we change the side lengths to be 2, and now our hypotenuse is 2 root 2 instead of just 1 root 2. This happens with all of our 45, 45, 90 triangles. Our ratio between our legs and the hypotenuse is 1 to 1 to root 2, meaning that I can scale this up however I want to. Okay, so let's say I have now side lengths of 3. Well, that means my other leg is 3, and my hypotenuse is 3 root 2. It's a ratio that needs to stay consistent with however I scale it up or down. I can even scale this to 65 by 65. So it would be 65 root 2. Or maybe I only know the hypotenuse, and I know the hypotenuse is 4 root 2. Well, that means that my legs have to be 4 and 4 to keep the ratio consistent. This is our special right triangle for 45, 45, 90 triangles. Our ratio is 1 to 1 to root 2. So when you see this isosceles right triangle, you can use this ratio to simplify things, to make your life a whole lot easier. Now let's look at an example with our 30, 60, 90 triangle. And in this one, I'm going to actually have to add a little bit to this triangle. I'm going to reflect this triangle and have the exact same thing on this side. So that we still have our 90 here, and on this side it's 60 because I reflected it, and this is 30. Meaning this entire angle is also 60. Meaning if I have 60 in all of my angles of this big triangle, this is an equilateral triangle. And if I reflected this triangle, then this side would also be 1. So if these sides of this equilateral triangle add up to 2, then this side must be 2, and this side must be 2. So really, when we're looking at our 30, 60, 90 right triangle, we are talking about half of an equilateral triangle. Okay, so I'm going to erase a little bit of this so that we can then figure out what is our smallest side. Okay, so that's how we figure out, okay, our hypotenuse has to be 2. Now what is our missing side? Now right now we have our smallest side, which is because it's across from the 30, this is our small side. I'm looking for my middle length side, the 60-degree one. I'm going to plug it into the Pythagorean theorem. I'm going to say 1 squared plus b squared is equal to 2 squared, which means I'm going to subtract 1 from each side and get b squared is equal to 3. And we square root and we get that b is equal to the square root of 3, meaning this middle length side is the square root of 3. Just like our 45, 45, 90 triangles, this is a ratio that stays consistent however I scale this up. So our ratio from smallest to largest side is 1 to root 3 to 2. So I could scale this up and say maybe my smallest side is now 2. Well, that means that I have 2 root 3 and 4 because I multiplied everything by 2. Or maybe I have now a side length of 6. 6 is my smallest side, so I now have 6 root 3 and 12. Notice that the smallest side and the biggest side, okay, going from the smallest to the biggest, it's always double. I multiply by 2. Or maybe I don't know the smallest side. I know the middle side. Maybe I have been given that we have 10 root 3 as my middle length. Well, that means that my smallest side must be 10 and my biggest side is 20. I just use this ratio in order to figure out what are my missing side lengths. Okay, I can scale this ratio up and down. So let's practice with a few different things. So we have a 30, 60, 90 triangle. Our smallest side is 5, which means my middle is 5 root 3, and my largest is 10. Okay, and you can just remember that 10, that's because this is half of an equilateral triangle, so it must be double of our smallest side. Okay, how about this one? Traffic sign is in the shape of an equilateral triangle. It has sides of 12 inches long. What's the area of the front of the sign? Well, remember that if we're finding the area of this triangle, we're going to need base times height divided by 2. And I know that my base is 12. Unfortunately, this dashed line, that's my height, but I don't know that yet. So, let's figure it out. And in order to find that, I actually am going to cut this into a right triangle. And we're going to say, well, if this is equilateral and I just cut it in half, that means that I have a 30, 60, 90 right triangle with a hypotenuse of 12, a smallest side, half of 12 is 6, so this height must be 6 root 3. So I can plug that into my formula now and say we have 12 times 6 root 3 divided by 2. Well, outside of that radical, we can multiply those out and get 72 root 3 over 2, or 36 root 3 inches squared. Okay, so using these patterns, we can find some pretty cool things. Okay, how about this one? A baseball diamond is a square with sides 90 feet long. How far does the catcher throw the ball when throwing from home to second? Well, that means that this is home and this is second. So it means that we are cutting this rectangle or this square in half, meaning we get 45, 45, and 90. So our ratio of 1 to root 2 is the one we're looking at. But now we know that we have 90 for each of our legs, which means that we have 90 root 2 as my hypotenuse, my longest side. So we would say it's 90 root 2 feet. Okay. All right. How many units is it from the origin to 2, 2 on the coordinate plane? All right, so if we sketch this really quick on a coordinate plane, we will say, all right, this is the point we're looking at. Well, if we drew a triangle here, we would say it has side length of 2 by 2. Well, that means it's isosceles right triangle. So we're going with our 1 to 1 to root 2. So we change that to 2 to 2 to 2 root 2. So how many units is it away? It's 2 root 2 units away from the origin. Alright, if each side of an equilateral triangle is 2 inches long, what's the area of the triangle? Well, if we have this equilateral triangle, 2, 2, and 2, that means that we are cutting this in half so that we can use our 30, 60, 90 ratio of 1 root 3, 2. And now we have, well, this is actually our unit triangle of 1, and our height is root 3 because our hypotenuse is 2. So in order to find the area, we use the base of 2 times the height of root 3, and then we divide by 2. So it means that, well, these can simplify. We have an area of root 3 units squared. Okay. A regular hexagon has sides of 2 feet long. What's the exact area of the hexagon? And then the approximate area. Okay, so a regular hexagon has sides of 2 feet long, 2 by 2, all the way around. Well, actually this relates to what we just did in this one, because we said, well, if we have a regular hexagon, all of those are equilateral triangles that make up the hexagon. So all of those are equilateral triangles with 2 by 2 sides. So each of those areas is root 3 units squared, and we have 6 of them. So we say that the exact area is 6 root 3 units squared. To get the approximate, then you would have to use the decimal of root 3, which we say that root 3 is about 1.73 times 6, so it's about 10.39 units squared, about. Well, I hope this has been helpful for your homework and for studying.